I'm in Minitab and I have the cholesterol data open, and I've just looked at the simple model, and now we're going to have a look at the more complex model for cholesterol where we include more variables. If I bring up the worksheet, you can see that we've got cholesterol, weight and age are all continuous, and then we've got gender and ab fat as categorical variables. I do have two coded columns. I was messing around with the data and I coded them to do something with, so I'll just delete those. Just delete. We don't need those. You often find this when you get data from other people, that they've been looking at their data in different ways and created lots of extra columns that they don't need. So it's difficult to do a graph of all of these things together because it's just too many different things to look at. Looking at two variables together is quite simple, and even three is manageable. Once you get more than three variables, it's not impossible, but it does become more difficult to read. So you can just do plots of variables two at a time just to show what's going on, but when it comes to drawing conclusions, it's best to do that through the analysis. So let's go back up to Stat, ANOVA, General Linear Model, and we will add all of these variables in. So I'm going to do this. I'm going to take that out. I'm going to add all four of those in there. So I've just put all of the variables in the model. I have to tell it which ones are continuous to make sure it does it fits the model the right way. So weight is continuous and age is continuous. I don't need to use the options, comparisons. So we did look at ab fat before, but we can look at it again now that we've got the full model, and we can also look at gender. Okay, graphs. I really wish it wouldn't keep putting that up on the other screen. So standardized residuals 4 and 1. And now that we've got two covariates, the weight and the age, we're also interested in looking at the residuals versus each of the variables. Now this is because if there are any problems with the residuals and we've got a complicated model, it can be difficult to work out where the problems are coming from. And if we don't know where they're coming from, we can't fix them. So if we plot the residuals versus each of the variables and there is a problem, such as there's a curve that we can see that we need to account for, or we don't have constant variance, if something else is going on, we're going to pick it out. We're going to be able to work out what's going on better if we have some separate plots. So I'm going to put in weight and age there. Results, that's fine. You can store things if you want to, we don't need to. Factor plots, now this is what we want. Now you can get these plots another way, and I'll show you that at the end. Now the main effects plots, we looked at this for abdominal fat where it showed us what the effect of the different levels of abdominal fat were on cholesterol on average. We also want to have a look at gender. Now the interactions plot, if abdominal fat has a different effect depending on which gender you are, then this is an interaction. So if abdominal fat is, say, more dangerous for men and raises their cholesterol more than it does for women, this would be an interaction. If abdominal fat has just the same effect on everyone, it's a main effect, and if it has a different effect depending on another variable, it's an interaction effect. And often we have both of these. So we'll put in an interactions plot for gender and ab fat. Okay, now to get that interaction into the model, it's not going to do it automatically. What we have to do is include the variables once for their main effect, and then we have to specify the interaction as gender and an asterisk ab fat. So that reads as gender interacted with ab fat, or people will say gender times ab fat. It's not actually multiplying them out. And this is our interaction term. If we don't put this interaction term in the model, then Minitab won't test for interaction, it'll just leave it out. Okay, right, lots of plots there, so we'll leave the plots till the end. Let's have a look at the analysis first. So we've got our general linear model, cholesterol versus gender and ab fat. It just puts the factors in here. So any continuous variables, your covariates, won't be listed under factor, and they shouldn't be. If you see any of your covariates listed under here with loads and loads of values over here, you need to make sure they're listed as, you need to run it again using it as a covariate. So we've got a different hypothesis for each variable in the model. So if I start off at the top of the list, the null hypothesis for weight is that there is no relationship between weight and cholesterol. We've got very strong evidence against that, and therefore there is a relationship between weight and cholesterol with all the other variables included in the model. The next hypothesis for age is that there is no relationship between age and cholesterol with the other variables in the model. And we actually have a really high p-value for this. So this is saying there is no evidence against that null hypothesis, and therefore we have no reason to believe that age is important for explaining cholesterol when we have accounted for the other variables. Now, if we just ran a regression of age on cholesterol by itself, and I encourage you to do that, you'll probably find that if you just look at it by itself, it is significant, but that's because the other variables haven't been adjusted for. Once we adjust for weight, gender, and abdominal fat, and the interaction term, then age is no longer important. So you can go through and run this model again without the age if you like. Then for gender, the null hypothesis is that there is no difference in cholesterol for the different genders. We've got strong evidence against that, and there is a difference in genders with the other variables in the model. Same for abdominal fat, and the interaction term says that the null hypothesis is there is no interaction between gender and abdominal fat when we have accounted for or adjusted for the other variables in the model. We have very strong evidence against that, and therefore there is an interaction. So abdominal fat is having a different effect depending on gender. Our R-squared adjusted is very high, it's about 95%, so we are explaining about 95% of the variation in the data with our model. You can ignore this. This is actually the regression equation for just weight and age, and it will look pretty much the same as what we've got up here. Grouping information. Now, this is similar to, well, it's the same as when we did an analysis of variance. If we find that there is a significant difference between different levels of abdominal fat on cholesterol, it doesn't actually say that every single level is different from each other. It just says at least one of the levels of abdominal fat is having a different effect from the others. And if we want to know which levels of abdominal fat are significantly different from the others, we need to look at these post hoc analyses, or the grouping information, and it says that means that do not share a letter are significantly different. So the mean level of cholesterol for those with severe abdominal fat is significantly different from those with some abdominal fat and low abdominal fat. So we've actually got three different groups here. The same with gender. Now, because we only have two groups, we know they have to be different from each other because they came out as significant. And the mean is the mean level of cholesterol. So you can see that with low abdominal fat, the mean cholesterol is 5.4, and this rises for each increase in abdominal fat. And with genders, we've got slightly lower cholesterol for females and males. So that's the analysis, and then we need to check our model assumptions. So if we look first at the residual plots. So our residuals are looking sort of normal. It's not perfect, but then it's a fairly small sample size. We might comment on that maybe there is a little bit of non-normality. It's possible this will disappear if we take age out of the model, because that was not an important variable anyway. The residuals do appear to be randomly scattered around this zero line, and there doesn't seem to be any evidence of increasing variance. It's possible there's a tiny amount of curvature in there. And the residuals versus the observation order, they look fairly randomly scattered about. So if there was curvature, it would show up in one of these other plots. So we've got cholesterol versus weight and cholesterol versus age. Now we've got these two observations down here on the weight one and then a great big gap. So that might give the impression of non-constant variance, but I think in this case it's okay. It's just we have these outliers. And in this case, age is not an important predictor anyway, so I'm not too worried about anything that shows up in this plot. And actually you can go through and run the model again without age, and then you won't need this plot. So I'm not picking up any big problems in these residual plots, and you do this, look at these the same way as we did when we looked at regression. Now this is the interesting part, the main effects for cholesterol and the interaction effects for cholesterol. And I said before that you can get these plots separately without doing the analysis. So if you lose your graphs and want them back, under ANOVA you can see down here it actually has an option to do a main effects plot and an interactions plot. So you can actually just do those without doing the whole analysis if you need to go back and check something. So we saw this before in the simple analysis that as your level of abdominal fat rises, so does your cholesterol, and we've got the slightly lower cholesterol for females and males. And this plot is nice because here you can see, if you've got a couple of categorical variables, you can see which one is having the big effect without actually going through and calculating effect sizes. It's obviously the abdominal fat which is having the big impact here, and this gender effect is very small. Now the interaction plot is showing us, is there a different effect of abdominal fat for the different genders? So we've got males in red, and we can see that the males actually started off quite low, but with the abdominal fat the cholesterol shot right up and then it went even higher. So we have that the abdominal fat is having a more severe effect on cholesterol for men than it is for women. The women aren't reacting to it quite so badly. So the fact that the men are having this these greater rises in cholesterol due to abdominal fat than women is telling us that there is an interaction. Need to be careful looking at interaction plots. Depending on the data, it's possible that you'll get an interaction plot which looks like there is a strong interaction, but actually it turns out to be not significant when you do the analysis. So I'd usually advise that you do the analysis first and then come back and look at the plots which turn out to be significant. And usually that's just due to scale or the amount of data. If you have very small sample sizes, effects can be misleading when they're plotted as averages, but it'll come out in the analysis that it's not significant if it's not important. So you can go through and run this model again, and you can take out age and see what that changes in the model, what it doesn't change in the model. And if you had any other variables, you could then go through and add them in one at a time or take them out one at a time if you were looking to find the best model for your data.